In this video, we will discuss about minimum array end. You are given two integers n and x. You have to construct an array of positive integers nums of size n, where for every I, nums of I plus 1 is greater than nums of I, and the result of bitwise AND operation between all elements of nums is x. Return the minimum possible value of nums of n minus 1. So what they are saying is that in the input we are given two integers, one is n and one is x. Now what we need to do is that we need to create an array of length n, right? And the array should be created such that if we do the bitwise AND of all the elements of that array, then it should be equals to this x, right? And also we need to minimize the last element of the array, right? And whatever is that minimized last element of the array, that you need to return as your answer, right? So in this particular case, if you see that n is given to us as 3 and x is given to us as 4, so one of the possible arrays that we can create is 4 5 6. So you will see that when you will do the bitwise AND of all these numbers, these will be equals to x, which is 4. And here the minimized last element of the array is 6. So this 6 is your answer. You can check that this is the smallest value that you can get in this particular case. So this 6 has to be returned as your answer, right? So now how are we going to approach this problem? Let's see that. So now question says that the bitwise AND of all the array elements should be equals to this x, right? Then what does it mean? What hint can we get out of this? So if you see, if let us suppose in binary I have an x which is equals to 10110. This is some hypothetical x, okay? I have written it in binary, right? So for the array elements to have their bitwise AND equals to this x, can I say that all these bit positions should be equals to 1 in all the array elements, right? Why? Because, so how does a bitwise AND work? So in bitwise AND, if there are two bits as 0, then the corresponding bit is 0, right? If either of them is 1 and the other is 0, then also it is 0. If both are 1, then only we get the bit as 1. Then that means at these positions, at these places, we should have the bit as 1 in all the numbers, right? So what I'm saying is, if let us suppose this is my first number, so it will have 5 places. Then this is my second number, this will also have 5 places. Then third number, and then fourth number, let's suppose, right? So now in all of these numbers, these positions, right? This and this, all of them should have 1. So here 1 1, then here 1 1 1, here 1 1 1, and then here 1 1 1, right? If at all these places 1 is present, then in the bitwise AND also these positions will be 1 1 1 only, right? So that is for sure that in all of my numbers, these places, wherever the bits are 1 in the binary representation of x, then in all of my numbers at the same positions, we should have 1 in all the numbers, right? Now, what about the other bits? How do we identify the other bits to create our actual numbers? So, if you see, for my bitwise AND of these numbers to be equals to this x, outcome of these places should be 0, right? Because only then our bitwise AND is going to be equals to x, right? So I am saying is that for these positions, your bitwise AND should come out to be 0. Now, when is it going to come out as 0? When at least one of the number is having this particular position as set to 0, right? So basically, this particular position will come out to be 0 only if there is at least one element out of this. If only there is at least one number out of these which have this particular bit position set as 0, right? So if I am saying that I will keep these two positions as 0 0. Now if you note here that it doesn't matter what is present at these positions. Why? Because here we have 0, right? So whatever is present here, that won't make any difference. This will always come out to be 0 and this will always come out to be 0, right? So now if you closely look here, that this number is nothing but x. both of them are same, which is 1 0 1 1 0. So I am saying that I will consider the first element of my array equals to x. Now, why I only considered the first element equals to x? Why I didn't consider any other element? So see, there is one more condition that is given to us in the question, which is that our nums of I plus 1 should be greater than nums of I, right? Then that means this n2 should be greater than n1, n3 should be greater than n2, n4 should be greater than n3, right? Then that means as we move forward, we need to increase our number, right? And other thing is that whatever is the last element of the array, we need to minimize it. We need to choose it such that it is as minimum as possible, right? So then that means as we are increasing our numbers, we would try to make minimal increase in our numbers so that the last element is always as minimum as possible, right? So if you would have taken, let's suppose, n3 as 0 0 here, then n2 and n1 should be smaller than n3, right? So in that case, you would have to change any of these positions as 0, which you cannot do. These bit positions have to be 1 only, right? So we can take the first element of our array equals to x, right? Now, how do we try to identify the other elements of our array? So what we need to do is that we need to increase our number as we move forward, and we need to make minimal increase, right? So that we can minimize the value of the last element, right? So in this, I need to make minimal change. So now if you closely look, these positions are always fixed, right? These bit positions always have to be 1. So I just only need to identify these two bits in all the numbers, right? So now what I need to identify is that what should I take the value of these two bits such that there is minimal increase in my number from n1 to n2, right? So now how will you identify that? So you know that as we move from right to left, the contribution of the bit increases, right? This bit has a contribution of 2 to the power 0. This bit has a contribution of 2 to the power 1. This bit has a contribution of 2 to the power 2. This has 2 to the power 3 and this has 2 to the power 4, right? So in these zeros, if you see, this is having a contribution of 2 to the power 0 and this 2 to the power 1, right? So since we need to make minimal increase in our number, we will try to change the bit which is having least contribution in our number, right? So out of these two, this bit is having less contribution, right? So we will change this bit, right? Because see, although we had multiple options, we could change this 0 to 1 and we could keep this 0 as is, or we could keep this as 0 and change this to 1, or we could change both of them to 1 1, right? But since we need to make minimal increase so that we can minimize the last element, that is why we are trying to change only the bit that is having the least contribution, right? So what we'll do is we will change this bit 0 to 1 and this will keep as is in our next number, right? Then in the next number, what we can do is we can change this 0 to 1, right? Now for this particular bit, if you will keep it 1 here, then you see there is one more number which would lie between n2 and n3, which you could take, right? Which is this number, right? So since you need to minimize the last element, then why do we need to skip this? Let's take this also. So we will make this bit as 0, right? And then for the next number, what you can do is that keep this as 1 and change this bit as 1. So now if you see that we have done minimal increase in our number as we are moving from n1 to n2 to n3 to n4, right? So now if you closely look here, if we look at only these bits that we are changing, so if you see, in this case, we considered 0, 0, right? These two bits, right? Then in this particular case, we considered 0, 1, right? In this particular case, we considered 1, 0. And then in this particular case, we considered 1, 1. Right? I am talking about these bit positions which we were changing, right? So now can you see a pattern over here? This 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3, right? So this can be anything. Our n can be anything. So this is the pattern that in n1, we utilize the number 0. These are the decimal numbers, right? So whatever were the bit positions that we were changing, at those bit positions, we used decimal 0 in its binary form. Then in n2, we use the number 1 in its binary form. In n3, we use the number 2. In n4, we use the number 3 and so on, right? So now if I tell you that you need to identify the third element, you need to identify n3. How are you going to identify it? So x is this, right? When x is this, you know for sure that in n3, these places are always going to be 1, right? You only need to identify these two bits, right? So I am saying you need to identify n3. Then in that case, you will have 5 bits here. These positions will always be 1. You need to identify these two bit positions, right? So now how will you identify that? So if you see, for n3, we were considering the number 2 in its binary form, right? For n2, we were considering 1 in its binary form. How are we getting this 2 for n3? So this 2 will be nothing but n minus 1, right? For n3, we are taking 2, right? So can I say it is n minus 1? So it will be 3 minus 1, that is 2. So when I want to find out n3, I will take the number 2, I will take its binary form, which will be 1, 0, and I will insert these bits at these places. And I will be able to identify the binary representation of my number n3, right? So what you can do is that you can take two variables I and j. So initially I will be here and j will be here, and then you will see that okay, this particular bit I need to change, so I will take this bit and I'll add it here, right? So 0 will be kept here, and then you will move both I and j forward, right? So now I will be here and j will be here. Now you will see that at this position we are having a 1, and this one I don't have to change, because if I will change this, then my bitwise AND won't be equals to x, right? So whenever we will see a 1, we will ignore it, we will move forward, right? So then our I will be here. Now again this is 1, so we will ignore it and we will move our I forward, so I will come here, right? Now at this position you will see that okay, this is not a 1, so I will take this bit and I will keep it here, right? So this 1 will come here. And at this point, you will move both I and j forward. So I will become here and j will be here, right? So if this number will be having some bits here, so it will keep on moving forward, right? In our answer, we need to return long, long. The return type is given to us as long, long. Our answer can be of 64 bits, right? Because we are given as long, long. So the answer that we have to return is can be of 64 bits long. So here you can have 64 bits. So you will keep on taking bits from here and you will keep them adding here, and at the end you will be left with the binary representation of this number n3, and then the only thing that you have to do is to convert the binary representation of n3 to a decimal number, right? For that what you can do is, so you know that the bit positions are, this is 0, this is 1, this is 2, this is 3, this is 4, right? So what you will do, this 0 anyways won't have any contribution, so for this you will do 2 to the power 1, then for next you will do 2 to the power 2, then 2 to the power 3, then 2 to the power 4, right? So with this you can convert the binary representation into the decimal form, and you will be able to identify the answer that you need to return. So what we did was that whatever was the x given to us in the question, we took its binary representation, we identified all the bit positions where the bit has to be 1, right? Then we started creating a number n3 where we initially kept all these positions as 1 because we don't want to change them. Next, whatever is the n given to us in the question, we considered n minus 1, we converted it into its binary form, right, which was this, and then whatever were the places that were need to be changed in our number, we took one bit from here and we added it here. And then whatever was the binary representation of the number that we have got, we converted it into the decimal form, and then we got our answer, right? So let's try to code it out now, and let's understand how are we going to implement this. So now, since our numbers can have 64 bits, we will create two vectors for storing the binary representation of x and n minus 1, which will be of 64 size, and initially the bits will be 0. So there will be another vector for n minus 1. This will also be of 64 size and the bits will be 0. Because in this binary x vector itself, we will add the bits of binary n. That is why we have taken its size as 64, because our answer can be of 64 bits, right? Now, since we need to find out the binary representation of n minus 1, so we will decrement n by 1, right? Now, we need to update our vectors, right? So what we'll do is, we will run a for loop from I equals to 0, I less than 27. and I plus plus. Now why 27? Because see, in the question constraints, the maximum value of x and n is given to us as 10 to the power 8, right? And 10 to the power 8 takes 27 bits in binary. So that's why we have taken 27 bits here, because all rest of the bits will be 0 only, right? And we have already initialized all the bits as 0. So we can run a for loop till 27 to update the bits of x and n minus 1, right? So inside this, what we'll do is, in the binary x at the ith position, we will check if the ith bit in x is set or not. If it is set, then at the ith position 1 will be present, and if it is not set, then at the ith position 0 will be present, right? And similarly, we will do for n minus 1 also, that if the ith bit is set in n minus 1, then take 1, otherwise 0, right? So now one thing to notice here is that our vector is of 64 length, right? And the indexes of the vector are 0, 1, 2, 3 and so on. And here we are checking if the ith bit is set or not. So our bits will be stored in reversed order in this binary x, right? So let me just tell you what I'm trying to say. So if let us suppose that the x is given to us as 4 and n is given as 3, right? Now 4 is written as 1, 0, 0 in binary, right? And its indexes are 0, 1, 2. Right. Now, when we are running our for loop, we are checking whether the ith bit is set or not, right? So what it will do is that if this is my vector, and it is having 0, 1, 2, 3, 4, 5 and so on indexes, then this 0 will be present here, right? This 0 will be present here, and this 1 will be present here, and rest others will be 0. So that is what I'm trying to say is that this x equals to 4 in binary is 1, 0, 0. Here the bits are 0, 1 and 2, but in the vector we have the indexes starting from 0, 0, 1, 2, right? That is why this 1, 0, 0 will be stored as 0, 0, 1 in our vector, right? Similarly, if you will see for n was 3, so we will take n minus 1, which is 2. 2 in binary is written as 1, 0, right? So this is the 0th bit and this is the first bit. So in your vector, it will be written as 0, 1. Why? Because the indexes are like this, right? So now what you need to do is that this is your number and this is your number. So as we saw here, that these two bits we were inserting at these two positions, right? Now these two are just reversed, we can say, right? So you can simply take these bits and you can insert them here, right? This is 0, so here this 0 will come. This is 0, so here this 1 will come, and rest of the bits will remain as is, right? In this vector also, we will have all other bits as 0, right? So if we are placing 0 at 0, then it is okay, right? It won't make any difference. So just that these two bits have to be set here, right? Then in your answer vector, what will happen is that you will have 0, 1, 1, 0, 0, 0 and so on, right? And the indexes will be this, right? So then when you will convert this binary to decimal, then what you will be doing? You will be doing 2 to the power 1 plus 2 to the power 2. Rest all the bits are 0 here, right? So it will be 2 plus 4, that is 6. And 6 is our answer in this case, right? So that is what I'm trying to tell you, that the implementation that we are following, in that these numbers will be stored like this in our vector, and we want to insert these two bits here. So we will start with I equals to 0 and j equals to 0, right? We will start from the starting of both the vectors, and we will check that if the ith bit of x is 0. If this is 0, then I should take the jth bit from this vector and insert it here, right? And if the ith bit is 1, then I will ignore it. I will move forward, right? So with that, what will happen is that for this 0 will come here. For this 0, this one will come here, right? So you will be able to get this answer. So that is why we will run a for loop of I and j. Both will be starting from 0, and we can go till I less than 64. Why? Because I will be moving faster than j. If there are more number of ones in this, then I will move faster. It will reach the end first, right? So that is why we will check for I less than 64, right? So we will create two variables, I equals to 0 and j equals to 0, right? We'll check that while our I is less than 64, then we'll check that if the ith bit in x is 0, right? If it is 0, then that means I should update it with the jth bit of n, right? So in the ith bit of binary x, we will keep the jth bit of binary n, right? And since we have taken this jth bit now, we will increase our j by 1. And in all the cases, whether our ith bit of binary x was 0 or 1, in all the cases, we need to increment our I by 1. So when you will do all these things, then in your binary x, you will be having your answer stored as 0, 1, 1, and then all other bits as 0, right? So now for converting this into decimal, you need to take a variable which will be of type long long. So let's suppose it is answer. Initially it will be 0. So now you will run a for loop of I equals to 0, I less than 64, I plus plus, and then inside this you will check that if the ith bit is 1 in binary x, then in the answer add 2 to the power I, right? 2 to the power I, right? And in the end you can return this answer, right? So if you see, this for loop is running 27 times, this loop is running 64 times, this loop is also running 64 times. All of these are constants, right? So can we say the time complexity is also constant? Yes, right? And for the space, if you see, we have taken two vectors here, binary x and binary n. Both are of size 64. 64 can also be considered as a constant, right? So we can say that the space complexity is also constant, right? So let's run this now. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please subscribe our channel.